So welcome everyone to our webinar today. My name is Ian Treviranus. I'm the product line manager for HORIBA's particle products in the Americas. I'm going to be discussing today how we can improve our trust that the size results we're generating are reliable and are as accurate as we want them to be. My contact information you see on the slide. So here's a general outline of what we're going to talk about. First off, I'm going to cover some general concerns, just some background information. Then we're going to talk about some of the technologies in today's presentation, and a phrase you'll hear me repeat several times called orthogonal techniques. And that's just a fancy way of saying different techniques that are suitable in the size range and for the sample type you have. And generally, if they give you very similar data, that you know it's reliable. Then we'll go through and we'll talk about how do you confirm size results for particles less than 1 micron. Same thing for particles greater than 1 micron, and then we'll get into the Q&A. So as a starting point, let's assume that your instrument is fully functional. That means that if you get a strange size result, that it's not because the instrument isn't working correctly. How you go about testing that we cover in a separate webinar and a technical note and perhaps even a white paper on our website. But the webinar is probably your best bet, and that's on the website coded as TR004. So it's called System Verification. And we also will assume that you have a suitable sample for the technology you own. Most of the people in the audience, I would bet, have a laser diffraction instrument. So you have to have a sample in the right size range, you have to have a sample in an appropriate concentration, a sample that can be dispersed well, things like that. I say here that counters are a classic example, so there's a technology called electrical sensing zone that kind of dominated the industry for decades a while back and became synonymous, just how Xerox became synonymous with copy machines. And the technology was so widespread that it was really used for a lot of applications that maybe weren't the best fit for it. And the other thing I'll say too is a lot of the questions that came in the pre-registration, the pre-webinar registration, dealt with a lot of more, how I would say, kind of usability, particle size training ideas. And we cover a lot of those in our 6-part bootcamp webinar series. And that webinar series is really focused on laser diffraction, but there are plenty of presentations. The particle size basics presentation, the sampling and dispersion, and the method development presentations are very general. Refractive index selection is specific to laser diffraction, but there's an awful lot of useful information there, regardless of the technology you use. So I would say that rather than spend a lot of time today talking about a lot of those, go look them up on the website. They're, again, in the webinars area, and they're coded TR1 through TR6. TR stands for training. Well, apparently I have animations on that slide. Didn't know that. Some more general concerns. So things that maybe we'll touch on a little bit but not get into too much depth today. Is my distribution really this broad? Or you could say it the other way, is my distribution really this narrow? So just in general, light scattering will broaden distribution. So any light scattering technology like laser diffraction or dynamic light scattering, they tend to broaden distributions. And in general, light scattering resolution is less than image analysis resolution. That's what IA stands for, image analysis. So it can be a fancy way of saying a microscope, or it could be a very descriptive way of a fully automated package. So really, any technique that will individually measure particles will be a higher resolution technique than the so-called ensemble measurements that measure many particles in a volume. I did get a few questions about how to best handle multimodal distributions. I'll discuss today a little bit about how you can test that different peaks may or may not be real. And for laser diffraction products and for a few of the other technologies, they have built-in multimodal reports. And if it does turn out that every mode in the distribution is real, generally you don't want to use the mean and the median of the entire distribution to be your key performance indicator, your product quality indicator, because the mean or median may show up right in the center of the distribution where there really aren't any particles, or it could just be very sensitive. So use the multimodal report to split out the different peaks and get statistics on each individual one. And then data matching is a topic all unto itself. We'll get into that a little bit at the end of the presentation today, especially when we discuss the cam sizer and matching sieves. But it is generally a truism that different instruments or different techniques will provide different data. And that's not something we as instrument vendors do because it makes for a good business. It's just the nature of the beast. If you have a centrifugal sedimentation device, it's going to be measuring something called the Stokes diameter, which is different than the equivalent spherical diameter a laser diffraction instrument may measure. So if those terms don't make any sense to you, there's a slide later on in the presentation that that helps explain that a bit better. So another common question was, I have an existing method, but I'm not really sure if it's giving me good data. And good can mean a bunch of different things. And typically our advice is to test the robustness of the method. Now, you can do that a bunch of different ways. You can tweak individual components of the method, like how long you make the measurement for. But really, in general, probably the best way to do it is just to start off by collecting multiple samplings. So far too often we're all very busy, and we take a little bit of a shortcut. So we'll take a sampling based off of the method, and we'll disperse if it's a powder based off the method. And then we probably put it in our particle size analyzer, and we might take one measurement, we might take 3 measurements in a row, but it's rare that we encounter users that will go back and do a second sampling and a dispersion, or a third sampling and dispersion, and really compare reproducibility. And that is a greater challenge than just repeatability. Repeatability is one sampling measured multiple times. And because it is a greater challenge, it's also a better measure of how robust your method is. And we would say evaluate the reproducibility by measuring the coefficient of variation of whatever your metric is. So if it's the D50 median or the D90 or the mean, measure the coefficient of variation. And we have a lot of material, again, on the website about how to do that. If you own an LA950, it'll do that for you automatically. And then finally, again, check with an orthogonal technique. Check with something else that's suitable and see if you get the right answer. Or the same answer, I should say. All right, so now we'll talk about the technologies themselves. So this is a short little description of all the technologies that HORIBA has to offer. So we're going to be talking about 4 different types today. We'll be talking about laser diffraction, dynamic light scattering, not the zeta potential aspect of it, dynamic image analysis, which is the cam sizer series, and then static image analysis, which is the PSA 300. We'll also be talking about using a microscope, too, if you don't have an image analyzer. So just a handy slide to keep on reference of different size ranges by techniques. And the next few slides are a bit more commercial. I'm not going to spend very much time on them. It's more for people that have never seen these instruments before. I will make a distinction that I'll talk about dynamic image analysis versus static image analysis, and the distinction is just what happens to the particles. So in a dynamic image analyzer, the particles are flowing past some measurement zone. In a static image analyzer, you're dispersing the particles onto some fixed area, usually a microscope slide, and then the slide itself moves. That's the distinction. So again, I'm going to go through these slides very quickly. There's a lot more to talk about. All right, so how do you confirm that your particle size distribution less than 1 micron is real? So there's nothing really special, nothing too special about this 1 micron distinction, except that that's a natural breaking point between dynamic light scattering, which really begins to suffer with material above 1 micron, and image analysis, which really begins to suffer with material below 1 micron. So technologies we're likely to see when we look at material below 1 micron. Laser diffraction is very common. Dynamic light scattering, extremely common. Ultramicroscopy, which is, for lack of a more descriptive term, it's kind of dark field microscopy. And then electron microscopy could be SEM or TEM. So if you have a laser diffraction analyzer and your distribution extends below 1 micron, how to prove that that less than 1 micron component is real? So the first option you have will be to filter. Filter the sample, you take out the large particles, and then you would remeasure with either laser diffraction or a DLS instrument if you have it. So DLS is the acronym for dynamic light scattering. And typically, if you have more than one technology, we'll always encourage you to confirm the results with the second or more technologies. And then just evaluate, is this a reliable measurement? And you'll see that on several of the different slides for several of the different options, and it'll mean something different for each technology. So a reliable measurement for laser diffraction, are you getting enough scattering signal? Can you reproduce the result? If you do multiple samplings, multiple filterings, can you reproduce it? So for this example I'm showing here, we had a bimodal sample, and we chose a 200 nanometer filter, took out all the big stuff, and this is what it looked like when we split it. So not that this is the most accurate distribution, but it does confirm that the submicron component is real. If it wasn't real, if it was some artifact of the algorithm, or if it was something else, this distribution should not appear after we filter it and remeasure it. Second option, run a sedimentation experiment. So the easy way to do this, if you have a beaker and you have a powder, is to create a sample, create a suspension or remove it from an existing suspension, and just let it sit overnight. Or if you have a centrifuge, you can speed up the process. And what we're trying to take advantage of here is the fact that very small particles will stay suspended longer by Brownian motion than the large particles. So what we're hoping is, if we start off with this suspension, all the large particles will sediment to the bottom like we see in this picture. And then what we're left with here is the supernatant. And so we sample just from the supernatant, and I say we very carefully sample it because we don't want to accidentally disturb this and draw up some of the big stuff that's sedimented out. And then again, remeasure with our laser diffraction analyzer, or DLS if we have it. And if we get a result that's reliable, then again we can say that we have the small particles there. Your third option is to use an electron microscope, either an SEM or TEM. More likely you'll have an SEM handy. Still not as likely as the other technologies, but more likely than a TEM. Some concerns with electron microscopy is that sampling is a bit more of a concern. Less of a concern when you're looking for particles below 1 micron, but still it could be a concern. It can confuse primary particles and aggregates. So in the image here, we'd look and we'd say, all right, we see a small particle that may be attached to this bigger particle, but it's hard to say for certain. Are they just sitting on top of each other? Or is it that you've decorated the larger particle with the smaller one? Are these actually joined together and can be considered the primary particle, or is it just a dispersion issue? It is, however, extremely high resolution. As you can tell, you're actually imaging the particle surface. There is no distribution broadening that's happening because of some scattering effects. It's a very nice solution if you have it. Fourth option, and relatively unique to laser diffraction, change the refractive index that you're using. So if you have a laser diffraction analyzer, depending on the wavelength of the larger light source, the longer wavelength light source, your particle size distribution will become very insensitive to refractive index above some critical diameter. So for the LA950 and most of the LA series from HORIBA, that critical diameter is about 25 microns. So if your distribution is larger than 25 microns, entirely larger than 25 microns, then you don't have to worry about refractive index because the scattering algorithm at that point kind of reduces to just the Fraunhofer approximation. Now again, if those words mean nothing to you, we talk about that in some light scattering theory webinars on the website. But suffice to say, if your entire distribution is greater than 25 microns, you don't have to worry about the refractive index. That said, if you have part of your distribution below there, and then you do have to concern yourself at least a little bit with refractive index. This is the most common question we get from diffraction users is, do I have the refractive index correct? What effect does it have on my distribution? I have some novel material. How do I know that the RI choice I've made is the best one? We have tools in the software to help you choose that, and we have so much content on the website. I think we probably have 6 or 7 or maybe even 10 different pieces of content. But the takeaway is, if you don't know what the correct refractive index is, at least choose one value and be consistent. As long as you're consistent with the value, the instrument, the technology still will show you when the distribution is changing. So you can kind of create a fingerprint of what good results look like, a good performing material looks like. And then if the size distribution begins to change, so long as you're consistent with the refractive index, you'll know if size directly relates to product performance or process performance, that because the size is changing, so will the performance. I give an example here that came across my desk a little while ago of the same result being measured in two different facilities, both in LA950s, but using different refractive indices. So in one case they're using 1.57 as the real term, and in the other one they're using 1.85, and they get two different particle size distributions. And the question that was posed to me was, which one's real? You know, is this small mode here below 1 micron, is that real or not? And you begin, because most light scattering instruments are a little bit of a black box, but you begin to question what's really going on inside the analyzer. And this is perfectly normal and very easily explainable. And it gets back to this relationship that's at the heart of laser diffraction analyzers, which is that large particles scatter very intensely at low angles, and small particles scatter very weakly at high angles. And so what that means is, if you use a larger refractive index is the way we think of light being bent as it passes through a material, so light changing angle. A higher refractive index is going to mean that the light should be bent at a greater angle than a lower refractive index. And so if you put in a higher RI term into the laser diffraction software, it will expect to see more light being scattered at higher angles, or wider angles rather. And so what the LA950 algorithm did here is, when it saw a high refractive index, and for most materials this is a relatively large refractive index, it saw some amount of light being scattered at wide angles, and it said, well, I have being input a very high refractive index, or a relatively high refractive index. And so I expect to see larger particles scattering more light at wider angles. Now, when it sees a smaller refractive index, like 1.57, it doesn't expect that the large particle component here will be scattering light at those wider angles, right? The lower refractive index means it's scattering at lower angles. And so instead it starts looking at it. It says to itself, well, this wide angle scattering must be coming from a population of smaller particles. And so the algorithm says, all right, I need to fit this light scattering pattern that the instrument just measured. What's the best possible fit with this one input of information? And the best possible fit is a bimodal distribution. So that's a long explanation of a very important principle. And again, refractive index is the most common question. If you have concerns along these lines, please contact me. I'd be happy to point you to different places on the website, or depending on how much time my son gives me at home, I can answer you directly as well. All right, moving on to a different technology. So if you have a dynamic light scattering instrument, how do you prove that the components less than 1 micron are real? So the first option I would say is, if you have a laser diffraction analyzer, run the same sample there. And I say that because DLS is exquisitely sensitive to the presence of large particles, and that's because in that size range, scattering goes to the 6th power of the diameter. Diffraction is still very sensitive, but it's less so. It only goes to the 3rd power of the diameter. So you're more likely to see small particles which may be masked by the scattering from larger particles. The most advanced diffraction analyzers have a detection limit down to 10 nanometers. That's the LA950. So you can get results if you have enough scattering from these small particles all the way down to 10 nanometers. You do need a greater sample quantity than DLS. DLS, the smallest sample cell I think I've ever seen for sizing, is right around 10 microliters, maybe a little bit smaller than that. For laser diffraction, the smallest sample volume I've ever seen for a non-paste material is 5 milliliters. And that doesn't mean that you need 5 mLs of sample. It means that you need to have a total volume of 5 mLs, which means you need to disperse your sample into at least 5 mLs. And in general, you need greater sample concentration for laser diffraction measurement than you do for DLS. That said, it's the easiest way to do it. This is a simple measurement. It's very fast. And if you get a result that's in any way, shape, or form similar to DLS, then you can trust the DLS result. Second option, again, is electron microscopy. This is just a copy of the slide for laser diffraction. Third option is to filter the sample. So if you have a sample and you run it in your DLS instrument and you get a result of 2 microns, let's say, and you think to yourself, well, this doesn't make any sense. I know I have nanoparticles, or I suspect I have nanoparticles. The easiest way to check if those large particles are masking the small particles is just to choose a filter and remove them. Remeasure and see if you get a new answer. All right. Now we'll talk about how do you confirm the presence of material above 1 micron. So again, likely technologies we'll see, again, laser diffraction, again, DLS. We'll also start talking about image analysis. So this could be if you have an optical microscope in your lab, or if you have a more advanced turnkey system like a dynamic image analyzer similar to the CAM sizer, or a static image analyzer similar to the PSA 300. Or it could be that you're using sieves. Sieves are still the most common particle size measurement tool on the planet. It's inexpensive. They've been around forever. It's very intuitive how to use them. They're everywhere. All right, laser diffraction results greater than 1 micron. The first option is use a static image analyzer. It could be a manual microscope, but manual microscopy is a much bigger pain. And typically does not make for happy lab people compared to an automated solution. So essentially what we're using it here for is to verify the presence of large particles, or if there's a shape effect, verify why there's a shape effect. So laser diffraction, so I'll talk a little bit more about the shape effect. Laser diffraction reports the equivalent spherical diameter, which means even if you have a needle-shaped particle, it's going to be taking the total volume of scattering from that needle-shaped particle, and it's going to kind of recalculate what the equivalent diameter of that particle would be if it was a sphere. So there can be shape effects if you're running significantly non-spherical particles. In the most extreme cases, if we have a high aspect ratio needle-shaped particles, we might even get a bimodal distribution from diffraction or DLS, where the smaller mode is the diameter of the needle. It typically tends to be a very narrow distribution, and the larger mode is a very broad distribution of the length of the needle, and that tends to be very broad because the laser is going to be capturing scattering information from all the different projections of the length. So if you imagine a pen in front of your face tumbling in all directions, there's going to be many different possible ways you can represent the length of that, and very few ways you can represent the diameter of it. A whole different discussion. That's just the crackerjack explanation. But why do we like static image analysis for this confirmation? We like it because image analysis is the referee technique, meaning if there's any discrepancy about large particles, they turn to a microscope. And we turn to a microscope because, very simply, seeing is believing. If you can, if you have a diffraction result that has your largest particles around 100 microns, and you're buying material from a supplier that's speccing the material as having largest particles around 90 microns, it may not seem like a big difference, but for the process, it could be a critical difference. You just put it under a microscope, capture an image, and say very simply, no, those 100 micron particles are real, or if you can't find them, then you readjust your diffraction method. And here's the basic process. So you capture an image, you do some thresholding to say this is a particle and that's the background. You could apply different filters, so you measure high roundness particles different than low roundness particles, and then you just get some distribution. And you need to be careful here because any technique that's measuring particles individually by default will be delivering that information on a number-based distribution, whereas laser diffraction and DLS are not number distributions. Laser diffraction by default is a volume-based distribution, and DLS by default is a scattering intensity distribution. So I'll have some slides in a bit to talk more about that. A second option, if you don't have a microscope or a static image analyzer handy, test the sampling and dispersion. So large particles are generally much more difficult to sample accurately than smaller particles. So again, if you get a distribution that has out of your laser diffraction analyzer that seems to have too many large particles, I'm sorry, not enough large particles. It could be just that your sampling needs a bit of tweaking. Very often, again, you're very busy in the lab. You need to get something done quickly. You'll get a sample. Could be a kilogram of powder, right? How do you sample what you may only need a gram or less of that powder to get a good amount of scattering and a reliable measurement from the diffraction analyzer? How do you remove that 1 gram max from the kilogram that you got into the lab? So that's a sampling challenge. There's all sorts of different sampling techniques. Again, if you're running short on time, most of us do grab sampling. That's just, you might tumble the jug a few times. You open it up, you put your spatula in there, and you just take what's on the top. That's not the greatest sampling technique. The best sampling technique we know of for powders is spinning riffling, and that's where you have some powder on a chute. The chute vibrates, the powder flows down, and this tray is full of little pie slices, and it's rotating. So the idea is, regardless of whether the largest particles come off the chute first or the smallest particles, because the pie slices are rotating, you're always going to have a representative amount. If you don't have a powder, if you have a suspension, the best sampling technique we know of is to put a little magnetic stir bar in there, put it on a stir plate, and then put your pipette somewhere between halfway and 2/3 of the way down from the top of the liquid to the bottom of the beaker, and then about halfway from the center of the beaker to the wall. Dispersion gets into it because if you're detecting large particles in your diffraction result that you don't expect, they may not actually be individual particles, they may be agglomerates of smaller particles. So in that case, you could try using different surfactants. You could try using some internal or external ultrasound to break them up. We cover all of these topics in much greater detail in the sampling and dispersion webinar coded TR005 on our website. All right, so let's switch to DLS. If you are getting a DLS result greater than 1 micron, how can you verify that? Again, use laser diffraction. Here we're taking advantage of the fact that diffraction, even though it's not as sensitive to large particles as DLS, it doesn't suffer from the sedimentation problem that DLS has. So if you're not familiar, how a dynamic light scattering measurement works is you're trying to measure the Brownian motion of the particles. So as the particles get larger and larger, their motion comes less from Brownian motion and more from gravitational settling. So the larger the particle gets, the more often the diffusion is coming from the fact that it's sinking than from anything else. And again, modern diffraction analyzers have a detection limit greater than 1 millimeter, so that's no problem. It's well within the wheelhouse of the technology. And again, you do need a greater sample quantity and a greater sample concentration, as we've discussed. Option 2, again, use a static image analyzer. Here you may have problems. Most DLS samples and most DLS applications operate in a much more dilute concentration regime than could be handy to use for a static image analyzer. Typically you want multiple particles, multiple detections in a single slide. Otherwise, you have to start stitching slides and stitching images together. There is a minimum number of particles you want to count to get a statistically significant result. So this could be an issue. But again, you do quickly verify whether the large particles are present. You run into a little bit of the same issue that you run into with the electron microscopy, where you could confuse aggregates for primary particles and vice versa. All right, image analysis. So here I'm going to talk mostly about the CamSizer series of products. So those are dynamic image analyzers. But this first option is applicable to both static image analyzers, or really even if you just have a microscope. The easiest way to prove that the large particles are real is just to save an image. So if you have a CamSizer, you can set it up so that by default the CamSizer doesn't capture every single image. If it did, you'd need to have a multi-terabyte hard drive because the images are so high resolution and they quickly fill up your hard drive, and you're taking so many of them. But you can tell the software to preferentially only save images that meet with particles that meet a certain criteria. So above a certain size metric and with a certain shape. So that's a very easy way of proving to your internal stakeholders if you have these large particles, or if all your large particles have a certain aspect ratio. Let's say all your large particles are needle-shaped or are cubic-shaped. Very easy, convenient way of showing that. Again, seeing is believing. There's very few arguments that are sustained after seeing an image of the particle. And here I just make a small point that manual microscopy can be subjective. It's, again, if you're hunting for a needle in a haystack, it's much nicer to automate the process so that if you capture 200,000 potential images of, let's say 500,000 particles, that's not something most lab people are going to be willing to do. Second option is, again, look at sampling and dispersion. As we talked about, large particles are more difficult to sample accurately. Large particles may also be agglomerates, so there's different things we can do here. If you're using a static image analyzer, typically you're going to be using an accessory or something built into the analyzer to help disperse the powders. Just try using different dispersion pressures, see if that gets you different results. You have to be a little bit careful there because sometimes you can turn up the dispersing pressure so high that you're no longer deagglomerating particles, you're actually breaking them. Similar options exist for the CamSizer XT. So the CamSizer itself doesn't have much dispersion capability. It only really works with free-flowing materials. The CamSizer XT adds a dispersing element to it, and it can be used for smaller micronized powders as well. And so then, again, just choose different pressures and see how that affects the data. Again, we talk more about that in the sampling and dispersion webinar on our website. So those are the different scenarios that I could think of that we run into very commonly in the applications lab here. Let's talk a little bit about expectations. So very often we are presented with an organization that has maybe an older instrument or an older technology, and they want to upgrade. And they want to upgrade for a wide variety of reasons, but they might have a certain expectation of what the size could be. Or it could be that they don't have a different instrument or they don't have a different technology, but they're trying to match the results they're getting with their supplier. So regardless of where the expectation is being set, it's very important to understand what's going into that. Why is there this expectation? Sometimes it's historical. Sometimes it just becomes institutional knowledge that product X has a median between 14 and 16 microns. And once it becomes institutional knowledge, it's awfully hard to change that expectation. Sometimes it's coming from a supplier. The supplier spec says that it should be between this and that, so that's where we expect it to be. That's why we bought it. Sometimes it's coming because of hope, right? We hope we have nanoparticles, so when we see a result that isn't nano-sized, we want to understand why that is. I'll also make the point that it's important to compare apples to apples. So I talked about this a little bit discussing the distribution bases. If you're taking a result from sieves, let's say, so sieves measure on a mass basis, right? So you put your sample on the top of the sieve stack and you shake it, shake it, shake it, shake it, shake it, and you get a different amount of material that's retained in each different sieve cut. So that develops a mass distribution base. And now you're trying to compare that to a CAMSIZER result or a microscope result, let's say in general, an image analysis result. That default distribution base is number because it's analyzing each particle individually. You can't get very far if you're comparing a number distribution to a mass or a volume distribution because they're looking at two different aspects of the same distribution. So in that case, you'll want to convert the number distribution to the volume or mass distribution, just so you can be comparing apples and apples. The other thing that's important too is understand a little bit about the type of particle you're trying to measure. So if you have, the trivial case is you're measuring spheres, right? Every technology should measure spheres the exact same way because every dimension, every different way that particle can tumble, every dimension that's presented to the measurement is the exact same as every other dimension. That's the rarest application, unfortunately. Most of the time we get real samples that look like this. And so if you have a sample that looks like this and you're measuring it in a sedimentation analyzer, again, you're going to get something called the Stokes diameter. And the Stokes diameter is going to be a representation of how this particle settles with some force being applied to it. So if you imagine a leaf, the leaf falling from the tree always orients itself for maximum drag, right? It sways back and forth and it falls more slowly than if a cannonball fell out of the tree. Same basic principle. It's simplifying it quite a bit. If you have a material that's measured in a laser diffraction instrument, again, it will take the volume of scattered light from this particle and calculate what the equivalent spherical diameter is. If you have a DLS instrument, it's calculating the hydrodynamic diameter, which is the particle surface plus whatever else that particle might be dragging along with it through solution. So if you've activated the surface, if you have something bound to the surface, or even if you're just dragging ions through solution, the hydrodynamic diameter will report larger than the other diameters. If you have an image analyzer, you have both a blessing and a curse. The blessing is that you get to choose which size metric you want to measure. The curse is you get to choose which size metric you get to measure. So you can get paralysis by analysis. But this is a fundamental point I want to make, is understand a little bit about the type of sample you're measuring. And if you have a size expectation, is it an apples-to-apples comparison? And if it isn't, then you should expect to get a slightly different size result. So I have 4 slides here that talk a little bit more about comparing volume distributions to a number distribution, but it's equivalent to any 2 different distribution types. So here we have 3 different types of beans, and this is an equivalent volume of beans. So when we put them in the graduated cylinders, we see again they have an equivalent volume. This is entirely different than if we do a number distribution. Here we have an equal number of beans, but we put them in the graduated cylinder and they're entirely different volumes. And it's such an elegant way of showing this. These slides come from our former user now, she's retired, Heather from the city of San Diego. She used these slides to explain why these differences existed to her coworkers, and I always have to thank her when I show these slides. They're do such a good job of explaining it. This slide just shows, again, in general, what happens when we convert from volume distributions to more basic bases. Typically, volume distributions, and for DLS, a scattering intensity distribution would be even coarser. They tend to get further and further coarser. This is a slide that's just for your reference. I list different technologies and what their default distribution bases are. We could talk a little bit about correlation. So if you do have different data from different techniques, you have to decide, do you need to match the data? And if you do need to match the data, how do we go about do that? So we would check that both tools are working correctly. And the most common case we run into is with the CAMSIZER product line, where we're trying to match Sieve results. And a lot of times the Sieve results or the Sieve specifications might be 10 years old, could be 15 years old. Sometimes the sieves themselves are 10 or 15 years old, and that's problematic in and of itself because ideally you want the sieve mesh to be perfectly square, and when you've been using the same sieve for that long, very often it is no longer square. And where that becomes problematic is eventually if you shake material on a sieve long enough, all the particles will have a chance to see all the different sieve openings. And so if a large particle eventually finds the largest sieve opening, it's going to pass through that sieve. And so what you end up with is sieve distributions that report smaller, finer, than what the cam sizer is reporting, because the cam sizer is actually measuring the particle itself, whereas the sieve is measuring the second smallest dimension, and if the sieve is worn, it won't even be doing that accurately. And so the general point here is your specification or is your expectation fair? Again, look at the history of how that was developed. So here the point about sieving is, again, the second smallest dimension is what you're measuring with the sieve. So if you have an M&M shaped particle, it's not measuring the kind of circular projection. It's not measuring the end-on projection. What it's actually measuring is how this particle will fit through diagonally. That's the second smallest dimension. The good news is, if you have a cam sizer, that the sieve correlation is very, very advanced. It is not just a multiplier that's being used on every size bin. It actually will take your sieve reference, provided it's good quality data from a good sieve stack and good sieving technique. It'll take those reference points, and because it's actively imaging the particles, because it's taking because it's looking at the particles directly, it will say to itself, all right, this is the shape of the particle. We're assuming that the sieve has a nominally square opening. How would this shaped particle fit through that square opening? So it's an intelligent correlation. It's not some kludgy multiplier that's being attached. It really does try and imagine how this particle fits through a sieve. And very regularly we do this sieve correlation with outstanding results. So here is a correlated cam sizer result to the sieve reference. That's the black asterisk. And it does very well. So this is a way, at least with the cam sizer, if you're trying to match a sieve, you can have your cake and eat it too. You get the much improved resolution and usability and really just ease of use of the cam sizer, where you can get a measurement in 4 minutes as opposed to a sieve analysis in 15 to 30. But you also get to make your plant manager happy, or your lead PI, where you're matching the historic expectation as well. So that's what I had prepared for you. This is a very deep topic, many different things we can talk about. And so if you have any questions, send them in now. I'll go back to the webinar software, and I will see what's been sent in already. So thank you very much. I'm going to leave this slide up. This is all of our contact information.